All right, welcome back. The second speaker today is Chenglong Yu from Tsinghua University. So he is going to tell us about commensurability of lattices in PU1N.
Thank you for the invitation and introduction. It's a great honor to speak at CMSA. I spend a lot of happy time here. All right, so today's topic is about commensurabilities for some lattices in PU1N. So first, let me introduce or recall the definition of Euler's hypergeometric functions. So Euler introduced a hypergeometric function as power series as follows. It can represent many classical functions. And the most important thing about this function is that it satisfies a second order differential equation. It's like this, and you have parameters A, B, C. Usually we will choose rational parameters. And another form of this hypergeometric function is this integral representation. Is also found by Euler. And from the integral representation, you can see that actually the integration has singularity at 0, 1, and x and infinity. So here, these two are just related by changing z to 1 over z. All right, so the differential equation has 3 regular singular points at 0, 1, infinity on the Riemann sphere. And from this, it's very natural to study monodromy of this the solutions to the differential equation. So we can take any analytic continuation of 2 linear independent solutions. Actually, they can always be represented as hypergeometric functions or multiplied by some other well-known functions. And the analytic continuation will give you a monodromy. Since it has 3 singular points, so it will give rise to a representation. So after analytic continuation, it's still linear combination of these 2 solutions. So it's a representation from pi1 to PGL2C. So Schwarz found that the monodromy is kind of related to properties of the solutions or properties of hypergeometric functions. So the first motivation is to study when these functions are algebraic functions. And he found that this is true if and only if the monodromy is finite. And he also shows that the inverse of the ratio of these 2 solutions can be single valued is equivalent to gamma being discrete. So the monodromy finite or monodromy being discrete is quite important or related to the properties of the solutions. So another study or some properties about monodromy we care is these 3 aspects. One is discreteness. So when gamma is discrete, it's always a triangle group. So what is a triangle group? So triangle group can be realized as groups generated by reflections. So you take a spherical triangle, Euclidean triangle, or hyperbolic triangle, and you take the group generated by even number of reflections with respect to those 3 sides. And the angle of this triangle are just pi times 1 minus c and some other numbers related to ABC. And this was found by Schwarz, and he also classified all the finite ones, since he cares about whether the hypergeometric function is algebraic or not. And the complete classification of discreteness or discrete triangle groups is done by Mostow and Knapp independently. And another aspect for those discrete groups is that whether it's arithmetic. So a discrete group or discrete lattice being arithmetic if the discreteness is provided essentially by Z being discrete in R. So I will not explain in detail about the definition, but it's essentially this one. And Takeuchi in 1977 listed all the arithmetic triangle groups. So there are 85 examples. And the last important thing about this classification is commensurability. So when two discrete groups are differed by finite indices, we say they are almost the same. So they will be both discrete or both arithmetic. So the rigorous definition is as follows. So we are allowing the conjugation in the group to change one of our groups, and we take the intersection, and we want the intersection to have finite indices in both groups. Then we say these two groups are commensurable. So the commensurability for triangle groups is very simple. It's related to the geometry of the triangles. So if you can have a tiling of a large triangle with some smaller triangles, then we can prove that those two groups are commensurable. So if the two triangles are related in this way, then we say they are commensurable, and it's equivalent to the commensurability of the triangle groups. So actually we can solve it. And in Takeuchi's paper, he also listed all the commensurability classes for arithmetic triangle groups. So that's the classical theory. Another generalization for hypergeometric function is studied by many mathematicians, and is written in this form. So we recall that the hypergeometric functions can be represented in some integral form. And here we are taking integration of one form still on the Riemann sphere. So we are taking x1 up to xn plus 3. These are n plus 3 points on Riemann sphere. And we are taking a differential form with some powers, with some rational poles in the denominator. And the path is from xi to xi plus 1. So actually we have n plus 2, those functions. And these functions can also have analytic continuations. Now the moduli space is just x1 up to xn plus 3. And we can always use PGL2C action to transform 3 of them to 0, 1, infinity. So the moduli space has dimension n. So the moduli is just this products or configuration space of P1 modulo PGL2 action. And we also require the summation of mu I to be integer in order to avoid any poles or any singularities at infinity. So you can also ignore this condition and you just add one more point at infinity. And the analytic continuations of those functions also give rise to representations. Now the representation is pi1 of q, and you can see that the pi1 of q is related to braid groups. So we have representations from braid groups to PGL n plus 1c. So here we are taking n plus 2 functions, but the dimension of the vector space generated by those functions is n plus 1, and later we will see why they have one relation. And this is a group we want to study. And in 1980s, Deligne-Mostow and Thurston obtained criterion on discreteness and arithmeticity of those groups. So the most important thing about this representation is that in many cases, is actually hyperbolic. It's called complex hyperbolic. So the richest case for triangle groups are hyperbolic ones. So you can prove that for spherical triangle or Euclidean triangle, in order to have discrete triangle groups, you will have some finite cases or some like one or two infinite series cases. And for hyperbolic triangle groups, it's actually a group inside PU11 or the automorphism of Poincare disk. So it will leave invariant a Hermitian form of signature 11 on solution space. So the solution space has dimension 2, so it will act on the Poincare disk. And Deligne-Mostow and Thurston obtained this criterion, similar criterion in higher dimensions. So when the summation of the mu I is equal to 2, so the singular ways has a summation equal to 2, then the representation will leave invariant a Hermitian form of signature 1n. So this discrete group, so this group, we have non-discrete ones. So this subgroup will be a group in PU1n, which is a projective group, keep the Hermitian form invariant, and it will naturally act on complex hyperbolic ball Bn. So complex hyperbolic ball Bn is all the lines inside this n+1 dimensional vector space, and those are the positive lines under the Hermitian form. So it will be a Hermitian symmetric space. Corresponding automorphism group is exactly this PU1n. All right, so why do we care? So I will explain a little bit about why this condition implies Hermitian form of signature 1n, why this is nature. So I will take a Thurston's approach. So this is quite related to the study of flat metrics on Riemann surfaces. So if you consider omega norm squared, you will find a flat metric on spheres since all the mu i's. So recall that all the mu i's are from 0 to 1. So the angles, conic angles at x1 up to xn+1 are less than 2 pi. So we call them convex conic angles. And Gauss-Bonnet will tell us if you have this conic flat metric, if it defines a flat metric, then all the contributions of the curvature comes from the conic points. And the mu I are exactly the deficits of those conic angles from 2 pi. So from Gauss-Bonnet, we have summation of mu I equal to 2. And you can cut the sphere using the geodesics under the flat metrics. You can connect all the integration paths from x1 to x2 up to, for example, up to x5. We have 5 points in this example. And you can form a developing map using omega, using this flat metric. You can stretch out this flat sphere and put it on a plane. So it may have some overlap. So let's say it doesn't have overlap, then this can form this 8-gon. And the edge or the direction and length of the edge are given by the integrations of the form omega from xi to xi+1. So you have f1, f2, f3, and f4. And you come back using f4, f3, f2, and f1, but you rotate some angles. And in order to come back, you have one equation or one constraint equation for f1, f2, f3, f4. So that's why the dimension is reduced by 1. So now the free variables, the number of free variables is 3 in this example instead of 4. And the Hermitian form is actually the area related to the length or the position of those edges f1 up to f4. So why it has signature 1, 2 in this case? So you can complete this eighth-gon to a square or a rectangle by adding these 4 triangles. So the area of the eighth-gon will be the area of the rectangle minus the triangles. So since area is positive, so when you minus the positive area, you add some signature in the negative part. So you only need to calculate signature for rectangle. And we know the area formula for rectangle is just product of the 2 lengths together, the length of the 2 sides together, and it has signature 1, 1. So the signature in this case is just 1, 1 plus a negative term, and you will get 1, 2. In higher dimensions or for more variables, you can also argue in this way. So it always keeps this area invariant. So you have invariant Hermitian form when you change the position of those points. So why do we care about this PU1N and some subgroups inside this PU1N? So let me mention some results. So first is the discreteness about those groups. The Deligne and Mostow and Thurston obtained a criterion about the discreteness. And from the discreteness criterion, you find 94 plus 10 tuples of mu. So in total, you only have 104 examples for n greater or equal than 2. And for n equals to 1 is back to the triangle group case. So it has infinite many examples. And for arithmeticity is a more interesting question. So one of the motivation for Deligne-Mostow and Thurston is to study non-arithmetic lattices in PU1N. So from this approach, they can find non-arithmetic lattices in PU12 and only 1 example in PU13. So in PU12, you have some examples, also finite examples, and 1 example in PU13. So why this is interesting? Because for other simple groups, there are either infinite many commensurability classes of non-arithmetic lattices. For example, for O1N, this is work by Gromov, Piatetsky, and Shapiro. And for other cases, if the real rank for the group is greater or equal than 2, then it's Margulis superrigidity. And for other 2 rank 1 cases, it's done by Colette and Gromov-Shen. So there's also some other constructions for lattices in PU12 by Basser, Hinsberg, Hofer. So their method is to construct complex hyperbolic balls, hyperbolic ball quotients using hyperplane arrangements in P2, and they can apply Miyaoka-Yau inequality or Yau's criterion for ball quotients, complex hyperbolic ball quotients. So in order to apply this, they need to hook up some topological constants related to hyperplane arrangements, and they need those the equality in Miyaoka-Yau inequality to hold. And there are some other work on commensurability classes of non-arithmetic lattices. So they were found in 2014 by Durox, Parker, Poppert in PU12. So they also have finite many cases, and 1 example by Korenberg, Heckman, Loyangha in 2005 in PU13. Actually, at that time, they didn't prove that their 1 example is non-arithmetic. It was later proved by Durox in 2017. It's actually non-arithmetic. So for general PU1N, whether you have non-arithmetic groups lattices for n greater or equal than 4 is still an open question. And whether you have infinite many of them for a fixed PU1N is still open question. So next, I will introduce the main topic today. It's about commensurabilities for those groups. So I will call this theory Deligne-Mostow theory. So there are some commensurability results, positive results given by Deligne-Mostow and Sauter in 1970s. So they found some commensurability pairs for those groups with different tuples mu and nu in PU12. So they also find that, or they also proved some explicit indices for those commensurability pairs. In other words, they can prove that what's the common subgroup inside those two groups, and what's the indices, the finite indices among those two subgroups. So their result is given by these two lists. So you have the freedom to choose the parameter AB in both lists. And actually, their result is not only for discrete lattices, they also hold for non-discrete ones. So how did they find these numbers, right? So those pairs were found by Mostow with computer investigation for fundamental domains of those groups. So he found many examples, and then he concludes that there may be a general pattern using those parameters. So are these all the commensurability pairs, or these are the positive results? But we also need some invariants to distinguish like different commensurability classes. So this was done much later in 2012 and 2013 by Kappes-Möller and McMullen. So they actually proved that those pairs given by Deligne-Mostow and Sauter are all the commensurability classes for non-arithmetic Deligne-Mostow lattices in PU12. So these are actually all the results for commensurability relations for Deligne-Mostow lattices in dimension 2. So their invariants to distinguish those commensurability invariants are the adjoint trace fields and the ratios of Chen numbers. And those ratios of Chen numbers is called Lyapunov exponents in Kappes-Müller's paper, and some other pairs or ratios used in McMullen's paper is more related to volumes for those modular spaces. So there are orbifold volumes for those spaces. So those ratios are actually quite similar to Hinsberg's study of proportionality of Chen numbers for compact and non-compact Hermitian symmetric spaces. So next, let me mention our work for commensurabilities. So this is a joint work with Zhiwei Zheng. He is also a colleague at Tsinghua. So we did this work this year when we were both back to Tsinghua. So we found some commensurability relations or a machinery to provide those relations with explicit indices. So those are commensurabilities for the groups arising from the Deligne-Mostow theory. They are not necessarily discrete. So those pairs works for general mu and nu. So in dimension 2, our machinery reprove or rediscover the results from Deligne-Mostow and Sauter. And in dimension 3, we found 2 infinite series of pairs. So those are the pairs given by these numbers, and the parameter A is chosen such that each parameter is from 0 to 1. So for n greater or equal than 3, we have some other like finite pairs of relations. So let me say a few words about our approach or our proof. So we study this from the study of modular spaces of cyclic covers of products of P1. So we are especially interested in those of Calabi-Yau type. So what are the cyclic covers? So it's some variety given by this equation, y to the d equal to f1 up to fk to some power, and here f1 up to fk are just the sections of linear series on P1 to the m. So it defines a cyclic cover. We have a cyclic group action on parameter or on coordinate y. So the natural action will decompose the cohomology of y by characters. So what do we mean by Calabi-Yau condition? So we decompose the cohomology according to character. So let's take the tautological character chi, and we have the middle dimensional cohomology hm of y corresponding to chi. And the Calabi-Yau condition is that the hm0, the Hodge number, first Hodge number is equal to 1, and the vector space or the Hodge filtration hm0 chi is generated by some differential form omega. So the period integral of omega, similar as the period integral on P1, we can also study period integral of omega. Now it's a higher dimension. So it gives rise to multivariable functions on the modular space of those cyclic covers. So what are the modular spaces? So we have the freedom to choose those linear those sections of line bundles f1 up to fk. So those are our modular space. So more precisely, it's a certain GIT space for linear systems on product of P1. And those multivalued functions, similar as Laurentilla functions, will give us monodromy representations. So we also obtain some criterion similar as the Gauss-Bonnet formula before to determine ball type period maps. So what are the conditions? So let's specify to m equal to 2 cases. So y is a cyclic cover, D21 cover to P1 cross P1. And we define the weights mu I to be AI over D. So you can always rearrange those parameters or change of coordinates such that mu I is also from 0 to 1. And the Calabi-Yau and the ball type conditions are as follows. So the Calabi-Yau condition is that summation of degree of Fi is the by degree of Fi is 3, 3. So it's a P1 linear system on P1 cross P1. So we have a by degree. And the weighted sum of those degree is 1, 1. So these are our Calabi-Yau and ball type conditions. So instead of just one condition in dimension 1 case, we have 2 conditions. And the asymmetric solutions to these 2 equations will give rise to commensurability pairs. So we have like 11 or something like that series of solutions. So let me give you one solution to these 2 conditions. So the solution is as follows. Also some question from the audience. So the ball type condition, let me say a few words about the last part. So it's a little bit confusing. So here, the Calabi-Yau condition means hm0 chi y is equal to 1. And the ball condition is that the Hodge structure on hm chi y is of ball type, which means the period domain for this character space is a complex hyperbolic ball. So it underlines a Hermitian form of signature 1, 1n, and the HM0 chi part will give you the positive line for this Hermitian symmetric for this Hermitian form. So the modular space for HM0 inside HM chi is just a complex hyperbolic ball. So one solution to the previous equation. So we want summation of degree equal to 3, 3. So we can take degree 2, 1, degree 1, 0, and degree 0, 1. And the conditions, the second condition is weighted sum equal to 1, 1. Then we have essentially one equation for those weights, and we have 4 weights. So from this, we can obtain a complex surface Y, and since it's cyclic cover to P1 cross P1, then we have 2 fibrations over P1, projecting to 2 components, and it will have 5 singular fibers. So in the picture, I illustrate all the curves defined by this Fi. So F1 has degree 2, 1. So it will be this curve actually of genus 1. So all the 4 curves has genus 1. And the other 3 curves are just vertical P1 or horizontal P1s. And what are the singular fibers or the singular values for the projection? So they correspond to the position or the intersection relation for these 4 curves. And you can see that F1 has 2 intersections with F3 and F4, and also 1 intersection with F2. So when you project down to the first P1, you will have 5 singular fibers. And on the other direction, you also have 5 singular fibers. And from the weights, you can actually have 2 independent or 2 free variables solving those equality for weights. And those 2 free variables will give you 2 parameters or 2 free variables in this A and B. So the weights when you project down will be like different weights. That's because the configuration you have in these 2 projections are different, or the solutions to the equation is not symmetric. And from here, we can see that these pairs or these 2 tuples are related to the results of Deligne-Mostow. So Deligne-Mostow and Sauter. So we recover their first pair using this surface. So this double fibration, how does this give us commensurability relations? So first, let me mention that those surfaces also appear in Mullen's work, but his construction is a little bit different. It's only obvious to see 1 fibration from his construction. So actually, many examples in his construction are the same, but you can only see 1 fibration from his construction. So it's hard to see why they are the same. So our approach can be seen as a continuation of Mullen's work. And why does this give us commensurability? So the period map or the modular space, the multivariable functions from the period integral can be seen as simply this iterated integral of functions of 2 variables. So we are taking integration on P1 cross P1. So we are taking this rational form with 2 variables, dx and dy. So when we integrate dx or dy, we will have the function can be reduced to a pair Laurentida integral. So two different orders will give us two different Laurentide integrals with mu and nu. And local toriality for those cyclic covers of Calabi-Yau type, so will give us finite maps for moduli of those Calabi-Yau type varieties to moduli appearing in Deligne-Mostow theory. So those local toriality also holds for cyclic covers, even though they are singular. And essentially, we can say that the Fubini theorem gives us the commensurabilities. And how do we distinguish those commensurability, different commensurability classes? So we need to introduce more tools from arithmetic, from number theory. So the arithmetic Deligne-Mostow lattices, so essentially the non-arithmetic ones are already classified by Deligne-Mostow theory, Sauter, and Kappes-Möller and McMullen, because they only appear in PU12, and in PU13 there is only one example. So our results to apply to Deligne-Mostow lattices, we only need to care about arithmetic ones. So in order to distinguish them, so their commensurability is actually related to those k-algebraic groups, isomorphism of k-algebraic groups. So this K is a real field of cyclotomic extension of Q. So in the Deligne-Mostow theory, for n greater or equal than 2, this is equivalent to those cyclotomic fields being the same, and all the Hermitian forms are conformal, so they can be determined by lattice invariance. One thing to notice, or one remark, is that for n equals to 1, actually this is no longer true. That's a very subtle point, because so the Hermitian forms are defined over those cyclotomic fields, but even though you have different cyclotomic fields, for example, for d equal to 4 and d equal to 6, you have different cyclotomic fields and Hermitian forms defined on different fields. Their corresponding algebraic group can also be the same. So in this case, we prove that for n equal or greater or equal than 2 in the Deligne-Mostow theory, this cannot happen. So this approach can distinguish commensurability classes for arithmetic cases, but it does not give commensurability indices. So we need to combine the results mentioned before from study of Calabi-Yau type cyclic covers. So that's all my talk, and thank you